Hey, what's up guys? Today we're going to be going over how to control a stepper motor with your Raspberry Pi using the GPIO pins. And I just wanted to explain the difference between GPIO.board and GPIO.BCM. Now BCM is going to actually be for the actual GPIO numbers. So that's going to be like, for instance, we're going to be using GPIO 20 and also GPIO 21 today. And we're going to be putting 21, but you can also see that there's a 38 and a 40 here that is the same number, but that's actually the pin number or the board number. So whenever you put GPIO.board, that's actually going to be the board number, or the pin number. And whenever we use BCM, that's actually going to be the GPIO number. Okay, so I got a demonstration right here of a 4-step stepper motor. And you can see right here that we have 2 phases inside of a stepper motor normally. Now you can see right now we have current flowing through these coils right here, which is all part of the same circuit. And the current is flowing in one direction. So you can see that we have the southern pole here and the northern pole here on the actual stator, and that's actually this outside right here. And you can actually see that the rotor aligns to the magnetic pole and actually align itself according to that. Now you can see right here we'll actually heat up the second phase, and you can see that we have current flowing in one direction, and you can see that we have the northern pole here and the southern pole here. And then we start with phase 1 again. The current's flowing in the opposite direction in this demonstration over here, so the actual magnetic pole of the stator is actually reversed, and that's the same for this over here, except it's for phase 2, the second phase. And you can just see up here, normally stepper motors have 2 phases. These phases are used to magnetize the stator, which is the stationary part of the motor. The rotor, which is the rotating part, aligns with the magnetic pole of the stator's magnetic field. Each phase creates a magnetic field in the stator with poles that are offset from each other. By energizing the phases sequentially, the rotors move step by step, allowing for precise control of the motor's position. Alright, so this is the controller that we're going to be using. This is the DRV8825, and a few of these pins we're actually going to have to learn a little bit more about just so we can hook up this thing properly. So you can see right here, these are the actual phases that I was referring to. So this is the A phase, and this is the B phase up here. And this is the voltage motor. Now this is just the voltage for the motor, so we're going to actually be putting the full voltage into here. And this is over here is going to be the microstep modes, and I'm going to get into more detail with that here in a bit. Now you can see the current limit. Every motor is going to have its own current limit, so we're going to have to calculate the VREF, because right here this screw on this DRV8825 is where we're going to regulate how much current we're going to allow to flow into the motor so we don't end up burning it up. And how we're actually going to do that is you're just going to take your rated current, which my rated current, or the max current that my motor's manufacturer allows for, is 1 amp, and we're just going to divide that by 2, and so the VREF is going to be 0.5. So what you'll want to do is just screw this until you, like in my instance, you're below 0.5, so it actually limits the amount of current that's going to be flowing through phase A or phase B. So I just wanted to show you guys real quick. This is actually how I have my stepper motor wired up. You can actually see my buck converter right over here. Now this isn't something that you're going to necessarily need, but I wanted to feed the Raspberry Pi off of my DC power supply. So I just took that, put the buck converter in here, and just made it change the 10 volts that I'm actually getting from my power supply to 5 volts, so I could feed the Raspberry Pi and also the actual controller with 5 volts. And you can actually see right up here the voltage motor pin right here is actually getting the 10 volts directly from my power supply. You can also see that our GPIO pins here are hooked up to the actual controller as well. And I'm just coming up here for a second. I just wanted to show you that this is our step pin, and this is our direction pin. These are also important. You can actually see down here, this is actually where our GPIO pins are actually hooked up to. And right here you can actually see that this is actually just a ground. Now these two right here, I haven't done too much research into this, but this is the reset and the sleep. pin, and you're just going to want to hook that up with a 5 volts as well to actually make that controller work properly. And another thing that's important is you're probably going to want to put a capacitor inside of this circuit just so that you regulate the voltage so it doesn't like spike or drop too much. That's especially important if you're actually feeding all the equipment. Like for instance, like the Raspberry Pi, you're not going to want that voltage to vary too much, otherwise they'll end up shutting it off if there's too much current draw from the stepper motor. Now here's the microstepping modes. Now this isn't necessary, but it does make the operation of the stepper motor a lot smoother. It makes it nice. It does take away some of the strength or the torque of the actual motor, but with how much it vibrates in full step mode, and at least with my stepper motor, it is very nice to have. So I'm going to get more into detail whenever I'm actually inside of the code, but you can see here if you have low, 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 that's going to be full step, low, low, high, that's going to be half step, low, high, low, that's going to be quarter step, and so on. And I'll actually go back up here, and these are the actual pins. So if a 1 or a 0 is actually going to determine what microstep mode you're actually in. Now for step angle, this is important because a lot of stepper motors are just rated in step angles, or they show you how many steps are inside of a stepper motor with step angle. So in my instance, I have a 1.8 step angle, so that is going to be 1.8 degrees of step angle. So that pretty much means every step is going to be 1.8 degrees. And I just had this little demonstration here, but and that's also important because you can tell with that information how many steps it will take to have a full rotation, full 360 rotation. So, and you can actually see that right up here. And you're just going to get that by taking 360 divided by 1.8, and that's how I got the 200 here. And you can also take that 200 divided by 1, and then say for instance you wanted to have this thing rotate in a second. You can do this, and you can see how much time in between each step you need to actually make a full rotation. Now this is some of the code that you'll need to know to operate a stepper motor. So this isn't necessarily code, but the GPIO pins, just general purpose input and output. Time, we're going to be using this. Now for DEF, this is similar to a method. It's just so you can run a block of code and it's reusable, so you can continue to run it through your actual script. For loop, we're going to get more into this with the code, but it's just iterate over a sequence of values until completion. A try statement, this is for pretty much error handling. A variable, this is just a value or object that is represented by a string. And Pi GPIO D is a daemon that manages GPIO operations. And I'll get more into that as well. Alright, I'm going to do this more once we're inside of the terminal, but I'll explain a little bit of this code right here. So you can see right here to start with, we have direction, and we have this set for GPIO pin 20. Now what we're actually doing with this is we're either setting it to a 1 or a 0, and that's actually what we're going to be outputting from the Raspberry Pi to the actual controller. And you can see right here that we're sending a 1 just like we did up here, the clockwise. So we're sending a 1 into this actual function up here, and we're actually just outputting that pin, outputting on pin 20 right here, a 1. Or for this instance down here, whenever we're actually calling this function, we're just setting direction to 0, and then we're just outputting that pin as a 0. Now for step, what we're actually doing here is we're outputting a high or a low. You can actually see right down here instead of that function that we're alternating back and forth from setting the pin 21 from a high to a low, and that's just going to be switching the magnetic field inside of the actual stepper motor so it continues to take step after step. And I explained clockwise and counterclockwise, so that's just for the direction. Alright, now for SBR, this is actually going to be just our steps per rotation. And you can actually see down here inside of this try statement, we're just outputting that to this function up here using this. And once we actually do that, we're using that inside of our for loop to see how many steps we need to take, or how many times we need to loop through this for loop before the script is done. So, and it's just going to iterate pin 21 high and low over and over again until it actually completes this steps per rotation, so the whole 200. So make a full 360. I'll get more into that once I'm inside of the terminal. So, all right, let's hop over there then. So to use your stepper motor, the first thing you're going to have to do is to find out where the coils are actually wired. And the easiest way to actually do this is just to use a LED and plug it into all the contacts for your actual stepper motor and turn the actual motor. If it lights up, you know that those two that are causing your LED to light up are a coil. So you can see the two outside wires on the right and the left are each their own coil. So you know that that's how we're going to have to wire that up. So one's going to be A phase and the other is going to be B phase. So the other thing that we need to do is we actually need to set our VREF, and I'm going to have a meter in the upper left hand side here, and we can just use a screwdriver here. Now we want this to be below 0.5. So you can see I started by turning in the wrong direction first, and then we'll just get that down below 0.5, and that should be good for our current limiting. Now you do want to have your controller off, everything off whenever you're about to plug in your stepper motor. You can see I almost plugged it in. You can end up frying the chip on the actual controller. So I did end up turning it off now, and then I can plug this in to the controller, and then I could turn on the actual DC supply. Now we can hop over into the code. Alright guys, so now that we're inside of the code here, you can see that I actually have 4 steps that we're going to be running through inside of that for loop right there. And you can see that all we're really doing with this is stepping, we're outputting on pin 21 high or low, and that's all we're doing to the controller. And you don't even have to put the direction pin if you don't want to, because it's automatically going to be 0, so it's only going to go in one direction. But you actually only need one connection if you only want to go in one direction. And you can see here I changed it to 10, and we're just going to be doing 10 steps here. And you could also see that we put 0.5 as the amount of time that we're going to sleep in between our highs and lows. So that's also good to understand. So if you want to speed it up, you just make that number smaller, and then it will just do each step quicker. So you can see we have 100 here and 0.05 in between our highs and our lows, and it'll just keep running through that until it's done. Once it's gone through all 100 steps. So you can see right here now we have 200. And we're using 0.0025, so this should be 1 full rotation, and this is going to be around 1 second for it to actually complete a full rotation. And you can also see that we have a direction pin now, so we can actually change that from a 1 to a 0 on pin 20, and now we'll actually switch our direction up. So now we changed it to 1, so we get a reverse rotation. And I'm using GitHub just to commit it and pull it, just to let you guys know. See, we're doing SPR for steps per rotation. You can see our delay is a lot lower now. And you can also see that we can just multiply our steps per rotation. So if we want 4 rotations, we just times that by 4. And we're actually putting that inside of that method up there, or that function. And we're able to call on that function and actually put them parameters that we actually do inside of our try statement. and we can actually just push that into the function, and then we can actually utilize those variables that we end up pushing to that function inside of our code that we have inside of that function. Like you can see, it's the same exact thing. The only thing is that we're actually using a function and not just running it one time. We're not just running that for loop one time. We could actually alter the variables and run it multiple times. Now you can see here, we got our microstep modes. Now I'm just going to end up plugging that into my Raspberry Pi here and then into the controller. And then I'll show you the differences of the different microstep modes. It is a lot like it sounds. Full step mode, you're going to have, say for instance, we were using 200 for a full rotation. If you use half step, that's going to be a half rotation. And if you use quarter step, it's going to be a quarter rotation, and so on. It's very nice to use. All you have to do is change the values that you're outputting on them pins to high or low, and that'll correlate with the numbers up there to actually select what mode you would like to use. So you can see this is full step mode right here. So I'm just going to change that to half step. Yeah, just change that M0 to a high. And you can see here we actually have a half rotation at the end. And I'll run through quarter real quick. So change that M0 back to a low, and then M1 to a high. And you can actually see we're doing a quarter step there at the end. Like I said before, that is weaker whenever it comes to torque, but it makes the vibration of the motor a lot less. You're actually going to want to run this sudo pi GPIO, and that way that we can actually use that library inside of this next bit of code that we're going to be using here, and I'm going to walk you through that. So we got 2.25 stepper. Yeah, you can see we imported that library using the same pins. The only difference is we're actually going to be using a switch pin. You can also see that we're using a PWM signal, and we're actually having the PWM signal so it's exactly half on, half off. So we're actually using a 128 duty cycle, and the frequency we're actually using a 500 pulses per second, and that's just going to alter the speed that we're actually going to be rotating our motor at, because the more pulses you have, the quicker the steps are going to run through the actual motor. So just in this scenario, if I put a 200 there, it would do one full rotation in 1 second. So I'm just going to plug that into pin 16 on my Raspberry Pi and put a switch in. I did end up screwing this up, so it took me a minute to get this working properly. You do want to plug the other end of this switch into the actual neutral or the ground. You can see I was second guessing myself, switched it up, and then I had to switch it back, but now you can see it working. Now right whenever you press that button, it immediately turns in the other direction. One problem with this is that you can actually skip steps, especially if you have some weight on the motor, like if you're turning a belt or something. So a lot of the time you want to actually slow down the motor before you actually rotate in the other direction. I'll show you a little function that I made here that does that exact same thing. So I actually step down the PWM signal and then speed it back up in the other direction. So you can see right here that I'm just using the previous switch state and running through a for loop, and every time I run through that for loop I'm subtracting 1, so the PWM signal is continuously going to drop until I actually reach 0. And then another for loop after that is going to incrementally step up the PWM signal until it reaches 500, which is what I have my frequency set to, and then it's going to actually return back to the try statement, or actually it's going to return back to the while loop and continue running like it was before, just in the opposite direction. All this code is going to be in the description, just so you guys know too. And you can see every time it runs that function, it's just going to say ramp. I have it printing ramp every time it runs through that function. And this one's a little bit quicker, and I also ended up using microstepping to make it a little less jerky whenever it's actually switching direction. And I also have it so that it doesn't step down to 0, it stops at 100 PWM. I'm pretty sure that's how I have it anyway. And it will actually start at 100 PWM. And this is actually how you end up outputting a 1 or a 0 with this pi GPIO pi GPIO-D. So it's pretty much the same thing, except we're using microstepping and we're actually not going the whole way to 0. And it also increases and decreases the PWM signal by 4 instead of 1. So it's a lot quicker. Well, hey, thanks for watching, guys. Hope you guys enjoyed the video. If you liked the video, leave a like. If you disliked the video, leave a dislike. And talk to y'all next time. Peace.